Hi everyone, welcome back. In this section we're going to introduce derivatives and integrals for vector-valued functions. So that is, we're going to introduce concepts of calculus for space curves. So just a reminder, any function that associates with a number t a corresponding vector is called a vector-valued function. We also saw that last section that if we are interested in computing the limit as t goes to some value a for a vector-valued function, that can be computed by computing the limits of the corresponding component pieces. So these are limits, 3 limits from calculus 1. Now that we have the notion of a limit in mind, we can now construct the definition of a derivative. The derivative of a vector-valued function, r of t, is defined to be the limit of the difference quotient, just how we defined derivatives in calculus 1. So it's the limit of r of t plus h minus r of t all over h. Geometrically, what are we trying to capture with this? So here's the idea. Suppose we have a space curve and we have a corresponding point on that curve. Let's call that point P. Now in order to talk about these points in terms of vectors, we need our coordinate system, and then a point would be described or given by its position vector. So that's some r of t. We can look at a point a little bit away from it, maybe a point over here. This could be our point Q, and that would be given by the position vector r of t plus h. So we moved a little bit away from our original point. And what the difference quotient above does is it constructs this difference, r of t plus h minus r of t. So that's the vector from P to Q. And that vector PQ is given by r of t plus h minus r of t. That vector, which we call a secant vector, so we call this the secant vector because it's passing through 2 points on the curve. So it's a vector that starts at one point on the curve and ends at another point on the curve. So we'll call this a secant vector. When we scale it by dividing by h, all that does is construct a scaled version of this secant vector. What are we interested in doing with that? Well, we are interested in noting what happens as h goes to 0. What does this vector pq over h, or in other words, r of t plus h minus r of t all over h, what does that vector do? So in terms of my picture, that's just a scaled version of the green vector, that pq vector. So what does it do? This vector approaches the tangent vector to the curve at the point P. So it's going to approach a vector that looks like this. That's our tangent vector at that point. So I'm going to zoom in a little bit on it. This tangent vector, therefore, is r prime of t. And so that's what we're constructing here. We're saying as that point Q sort of slides along the curve and gets closer to the point P, this vector from P to Q, it starts to shrink, but we are scaling it, looking at a scaled version, division by h, so that as h gets smaller, we're dividing by a really small number, which in some sense makes this vector at least a reasonable length as we start to shift q along to p, or let h go to 0. And that green vector then approaches the tangent vector to the curve. So that's our derivative and our geometric interpretation of what the derivative is as a tangent vector. Now how do we actually compute the derivative? Well, since limits are computed component-wise, differentiation can be done component-wise. So we'll go ahead and we'll sketch a little proof of this fact down below that says if I have a vector valued function made up of components f of t, r of t, and h of t, then the derivative of it is just obtained by computing the derivatives of the individual components. So that's what we mean by component-wise differentiation. Why is this the case? This is just following from the definition of the derivative. So it's the limit as h goes to 0 of r of t plus h minus r of t all over h. But in terms of components, that's the limit as h goes to 0 of f of t plus h minus f of t all over h, g of t plus h minus g of t all over h. And I'm running out of room here, so I'm just going to have to shift this stuff over a little bit. See if I can squeeze it on in there. And that last component is h of t plus h minus h of t. Okay, bad choice in use of variables here because I'm using h both as this incremental change in t, but also as the name of the function for the third variable. Hopefully that doesn't add to too much confusion here. But the idea is that now we compute the limit of this component-wise. The limit of the first piece, that's just the definition of the derivative, f prime of t. And the limit of the second piece is g prime of t. And the limit of the third piece is h prime of t. And so that's the end of our proof, and that shows that we can compute the derivative by just doing derivatives of each of the individual components. So let's have a look at an example of this. We want to find r prime of t for this particular vector valued function. So to compute r prime of t, we just have to compute the individual derivatives. So the derivative of the first component, the derivative of the second component, and the derivative of the third component. The derivative of the first component, we'd use a chain rule here because there's a cosine of an inside function 2t. Derivative of cosine is negative sine 2t times the derivative of the inside function, which is 2. The derivative of t, e to the t, that's a product rule. So the derivative of the first, which is 1, times the second, plus the first times the derivative of the second. And then the last one is a quotient rule. Derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. We could try to simplify these things, but we were just asked to compute the derivative, and in general, unless we're going to do anything with it, we can just leave it in its sort of unsimplified form. So there's our derivative. It was just 3 calculus 2 derivatives that we needed to compute, 1 for each component. Now in terms of the geometric interpretation of the derivative r prime of t is also called the tangent vector to the curve at that point, r of t, provided that r prime of t exists and is non-zero there. So this is our picture that we have. There's our curve. Here's a point on the curve. And if this curve is given by a vector function r of t, then at this point on the curve we get tangent vector given by r prime of t for various values of t. As I move along, for each value of t I get a different point on the curve, and r prime of t for whatever value of t gives me that point, that gives me the tangent vector there. So this is the tangent vector at that point. Once we have a tangent vector and a point, let's call it point P there, then we can get a tangent line. So we have our point, we have our tangent vector, and therefore we can get our tangent line. So there's our tangent line. We can also take the tangent vector and just normalize it, make it unit length, and in that case we call it the unit tangent vector. So that's obtained by taking r prime of t and dividing by the length of r of t. Alright, let's take these ideas and work through an example, and then we'll end with a visual for this example and see that our calculations give us what we expect in terms of the geometry of the situation. So we want to find the parametric equations of the line tangent to the helix at this particular point P. So I've got this point P on this helix. The first thing I'm going to notice is that what value of t is it that produces this point on the helix? Well, if I compare, cos of t has got to be -1, sine of t has to be 0, and t has to be pi. Okay, so this corresponds to t equals pi. So r of pi is producing this point. So in other words, i.e., t is equal to pi. That's the corresponding value of the parameter that produces this point. I'm interested in finding parametric equations for the tangent line. So I'm going to look for the tangent vector first. So we'll start with r of t is equal to cos of t, sine of t, and t. R prime of t is negative sine of t, cos of t, and 1. And therefore at t equals pi, we get that r prime of pi is equal to negative sine of t, so sine of pi, that's 0. Cos of pi is -1, and the third component is 1. So that tells me then that the tangent vector to the helix at P is that vector there, 0, -1, 1. So now we can go ahead and we can construct the tangent line. To construct the tangent line, I need to know a point, which I have, -1, 0, pi. I need to know a direction vector, which I have. That's what I just computed using the derivative, 0, -1, 1. And so we can go ahead and construct the line. So the vector equation for the line, I'm going to change the name for this function now, the vector valued function that gives this line, because I've already used r for the helix, so I'm going to use L for line. And so this is our point plus t times the direction vector. Or in other words, it's -1 plus 0t, 0 minus t, and pi plus t. So there is our vector function, which gives the line. If I wanted to write down parametric equations for the line, then I'll just go ahead and pull off the individual components. X is equal to -1, y is equal to -t, and z is equal to pi plus t. And so there we go. Let's see that we actually got the right results in this case. So we'll go to math3d.org. I'm going to remove the default construction. We'll go ahead and we'll plot a parametrized curve. In this case, I want to put the helix out. The helix actually is the default parametrized curve. We can see it there. What do I want to do with the helix? I'm interested in a particular point on the helix. That point is -1, 0, pi. I'd like to construct the tangent vector to that point on the helix. I have constructed the components of the vector already. The vector is going to be 0, -1, 1. And you'll notice that it's plotted it starting from the origin. I'd really like that vector to be attached to the point. So a couple of things I'm going to do. First, I'm going to change the color. Maybe I'll make it red. Then I'll move it so that the tail of it is at that -1, 0, pi. And there it is. There's our helix, our given point P, and now we've just constructed the tangent vector there. And that's looking pretty good. It's looking pretty good. We can see as the point sort of zips around the helix and comes to this spot here, that's the direction that the point is moving in right at that instant. That's what the tangent vector is telling me. Now I'd like to construct the line, so we'll go ahead and we'll construct parametrized curve. This is going to be our tangent line, so we'll go ahead and write this in just to remind myself that this particular parametrized curve is the tangent line. Maybe we'll change its color to green. What is our equation for our tangent line? We worked that out. First component was -1. Second component was -t. Third component is pi, so I'm just typing pi, and then it auto changes it, or auto recognizes that it's the Greek symbol pi and inserts it in place, and so that's pi plus t. So there's our tangent line. All that's looking good. The one last thing you might notice is you can kind of see that the vector and the line, they have a hard time trying to decide which one wants to show itself. They're sort of battling for, do they want to show me red or do they want to show me green? And so the idea is that whatever one I want to bleed through, I can force it to do that. So I'll use Z bias here under the properties of the vector, and I'll just bump that up to a 1. And that gives it priority. So it says if there two objects are overlapping, show me the one with the higher bias. The Z bias means Z in this case is closer to the eye, not the Z axis. This is more about screen geometry, and so that way it shows me the vector without having to sort of fight with the green of the curve. Alright, so there we go. We've constructed our tangent vector at the point and our tangent line at the point. Alright. This leads to our next definition. This is the definition of what it means to be smooth as a curve. So a curve given by a vector function on an interval I is called smooth if the derivative is continuous and it's non-zero. So the derivative's got to not be 0. Let's check. Is this curve smooth? Is it a smooth curve? Well, we'll go ahead and compute its derivative. That's 2t, negative 2t, and negative sine t. And we just need to check. So each of these components is continuous, so that's great. Is the derivative non-zero? Well, no. Unfortunately, we notice that for the value t equals 0, we get the 0 vector out. So therefore, the curve is not smooth. There's an issue at 0. The derivative is actually 0 there. So how do we envision this? How do we visualize that this wasn't smooth? What's the reason for it not to be smooth? Why would we take this as our definition for a curve not to be smooth? Well, let's go ahead and look at a visual. So here's our curve drawn. You can ignore that red point for the time being. So there's our curve. You might say, well, it doesn't look like it shouldn't be smooth. I mean, it looks pretty smooth. So there's no abrupt bends in it or anything. Well, it turns out that in order to see smoothness, we have to think of motion happening. So this is really about the derivative, r prime of t, and the derivative is about how the points change along the curve as the t value is changing. So in order to see motion, what I've done is I've put a slider in here and I've just let the point get traced out for various values of the slider. So when t is negative, getting closer and closer to 0, we can see the point getting traced out there. And then as t gets bigger and bigger and bigger away from 0, you can see it's flying in the other direction. So it's coming in, and then it turns around at 0 and goes out. And it's really a question, the smoothness is really a question about the derivative. So I'm going to plot the tangent vector at each of those points. And let's see what happens to the tangent vector. We'll zoom in closer to 0 because that's where the fun stuff is happening. So as we come in closer and closer and closer to 0, the tangent vector disappears. It becomes 0, and then it goes in the other direction. So this non-smoothness is really happening because the particle is traveling in one direction, and then boom, it switches to be traveling in the other direction. So there's sort of an abrupt change in direction here, and that accounts for the non-smooth behavior of the curve itself. Alright, let's have a look at some differentiation rules. So much like with Calculus 1, when we introduced the derivative, we had differentiation rules that helped us compute it. In this case, we also have differentiation rules for derivatives of vector-valued functions. The derivative of a sum is the sum of the derivatives. The derivative of a scalar times a vector-valued function is the scalar times its derivative. We've got a couple of different products because there are different ways to take products using vectors. So we can take a scalar times a vector. That's property C. It says that we can use the scalar multiple rule, which says it's the derivative of the scalar times the vector plus the scalar times the derivative of the vector. Or if we had two vector-valued functions and we were dotting them together and I wanted to take their derivative, it would be the derivative of the first dot the second plus the first dot to the derivative of the second. Similarly for the cross product, we have a cross product rule. All very similar flavor to the original product rule we had. And that's not surprising because the way we compute the derivatives is just component-wise. The x component, the y component, and the z component. So a lot of the properties that we had from Calculus 1 carry forward through to here. If I have the derivative of a vector-valued function where it's u composed with some scalar function f of t, we have a chain rule that says it's the derivative of the outside function evaluated at the inside times the derivative of the inside function. So let's use these differentiation rules to prove a result. What we want to show is that for a differentiable function r of t that's of constant length, the tangent vector is always orthogonal to the position vector. So let's go ahead and prove that. So to start with, we have that r of t has constant magnitude. If I was to square both sides, then what I get is that the square of the magnitude is constant, but the square of the magnitude is the dot product of r with itself. So that's the first equation that I'm going to really use. R dot r is equal to c squared. Because now if I differentiate, then what we get is d by dt of r of t dot r of t is equal to the derivative of c squared. What's the derivative of c squared? Well, that's 0 because it's a constant. What's the derivative of the dot product of r with itself? Well, here we can use the dot product rule. It's the derivative of one of the pieces dotted with the other one, and then vice versa, added to it the derivative of the other piece dotted with the first one. And since the dot product is commutative, what this really boils down to is r prime of t dot r of t plus r of t dot r prime of t, but that's just the same thing. So this would be 2 times this is equal to 0. But then I could divide both sides by 2. So I could really cancel off that 2, and I get that r prime of t dot r of t is 0, and that means that r prime of t is perpendicular to r of t. And that's what we wanted to show. So starting with the assumption that r had constant length, we got the conclusion that the derivative is orthogonal to the position vector. Now what this really means, if you might be thinking, well, how do I know when r of t is of constant length? Well, what this really means is if r of t is of constant length, it means the curve lives on a sphere. Because a sphere consists of all points that are of constant distance from the origin. whatever the radius of the sphere is, that's their distance to the origin. So a sphere of a particular radius consists of all the points that are of the same distance from the origin. So if a function r of t has constant length, it means that the curve that it represents lives on a sphere. And so what this result says is if you have a curve on a sphere, then the tangent vector to the curve is always perpendicular to the position vector of the point on the curve. All right. Now let's get into integration. And in this case, if we just think about what we did for differentiation, all differentiation was done component-wise. So we differentiated x, y, and z components individually. Then when we talk about integration, again, this is going to be done component-wise. The integral of a function r of t, we do it by just integrating each of the individual component pieces. So we just refer to this as integration is component-wise. And in particular, we can extend the fundamental theorem of calculus then. Because what this means is that in order to integrate r of t dt, I just need to integrate the individual components, and to do those I just need to find antiderivatives, and so I can compute the integral of a vector valued function by finding an antiderivative of the function and evaluating it at the endpoints. So r of b minus r of a, where r prime of t is r of t. In other words, where big R is an antiderivative of little r. I'm just going to fix this word where because it looked a little messy there. So let's have a look at an example. We want to find the vector function r of t where r prime of t has these components, and also r has that initial condition, that r of 0 is 1, 1, 1. So from this, we can just integrate term by term. And we get that r of t is equal to the antiderivative of t squared is 1/3 t cubed. The antiderivative of cosine is sine of t. The antiderivative of e to the t is e to the t. Of course, when we compute antiderivatives, in each case, there's this constant of integration that happens in each case. I can pool all those together as to the components of a constant vector. So that's what C, the vector C is. It's just the individual constants of integration all brought together into one vector. And so now what do we want? We want C such that r of 0 is equal to 1, 1, 1. That's the condition we want to satisfy. That's that bit right there. That's what we want it to satisfy. So what is r of 0? Well, we've just constructed what r is. So plugging in 0 in, we get 1/3 of 0 cubed, sine of 0, and e to the 0, plus this constant vector c is equal to 1, 1, 1. And so that tells us that c has to be 1, 1, and 0. And so therefore, we've now managed to construct that function r, it's 1/3 t cubed plus the first component of c, so plus 1, sine of t plus the second component of c, and then e to the t plus the third component of c. And so there's our function, r of t, and it is precisely the function that has the property that when you differentiate it, which you can do, just a quick mental check, when you differentiate it, we get t squared cos t e to the t, and that's exactly what we wanted. We wanted it to differentiate to give us that. And when we plug t equals 0 in, we get 1, 1, 1. So not only did we find the result, we actually double-checked that it is indeed the result we wanted. Alright, that's it for this section. Thanks very much for watching, and we'll see you in the next section.